Okay, cool. Well, hi everyone. As you can see, today my topic is modern Objective-C exploitation. Before I get started though, just a few words about who I am. My name is Neil Archibald, or Nemo, and I'm a member of the group Feline Menace. I'm currently working as a security researcher for Archibald Labs and the vulnerability research team, which is pretty lucky because I get to do this stuff full time, so I'm really grateful for that. I've had an interest in macOS systems internals and exploitation for like, I don't know, 14 years now, which makes me feel kind of old. So the reason I'm making this paper, this talk, in 2009 I published a paper called Abusing the Objective-C Runtime in Crack. And basically what this paper did, it documented some Objective-C internals at the time, and then demonstrated, It demonstrated a technique for exploiting dangling Objective-C message sends, which we'll look at in a little bit. And recently I noticed people were talking about my paper a little negative, and rightly so. It was a little out of date, so I decided to step up and defend my honor and produce some new content around it. So for anyone who is unfamiliar with Objective-C, it's the language of choice on macOS X and iOS right now. There is a new language, which is an interpreted language called Swift, which is Apple planning to replace, or to augment this, I guess. I don't really cover Swift in this talk, but Swift is just a sort of interpreted language wrapper that lets you call into Objective-C internals, and it'll be a very long time before people stop using Objective-C libraries and stuff with that, and all these constructs kind of exist in that bridge anyway, so you can just kind of assume this stuff will still work. So Objective-C is an object-oriented superset of C, and that means that a Objective-C compiler can compile any C code that you throw at it. And the way they implement the object-oriented side is with this Smalltalk style messaging syntax, which a lot of people seem to hate, but I don't really care either way. And you can see an example of a method call down the bottom, and it's calling the alloc followed by the init methods to create an object called foo, right? So at a lower level, everything in Objective-C gets proxied through this one function called Objective-C message send. And that's really confusing the first time you ever like fire up IDA and go to reverse the Objective-C binary, because you just see like functions with one call repeatedly to the same thing over and over. And the way this works, so if you look at like a method call broken down, Objective-C message send takes the first parameter, a receiver, which is a pointer to the object that you want to call the method on the heap, followed by a selector, which is just a C-string method name, but it's not any C-string. You actually have to have the correct C-string that was registered with the runtime when your library loaded or whatever, and that's why that @selector syntax is there to explain that, I guess. And then the function has variable arguments, so after that selector is just all the arguments that you would typically pass to the method, right? Okay, so here's a logic diagram of how Objective-C message send works, still at kind of a high level. So the first step that Objective-C message send makes is to retrieve the ISA pointer, and that's at the very start of the object footprint. Funnily, I actually spent about 10 years calling this the ISA pointer before I met a real Objective-C programmer who was like, what's the ISA pointer? That's ISA, as in this class is a NS object, but I felt kind of stupid for getting that wrong for so long. So next it reads from the class struct itself the cache pointer, and that's a pointer out to this cache on the heap of methods that have already been called on the object, right? And then it needs to figure out an index into that cache, and it does this by taking the selector pointer, so that's just a pointer to the strings table of wherever the selector was stored, shifting it right by 2, and then ANDing with a mask that it gets from the class struct, and then it takes that index that it's generated and indexes into the cache. And it compares the pointer value at that location with the cell value that was passed into Objective-C message send. And if those pointers match, it calls the method because it found the right hit. Otherwise, it increments the index and tries to walk the cache. So the cache is basically a hash implementation. And so because everything's getting proxied through this one function, you get this construct happen a lot. And it happens under a variety of different vulnerability constructs, I guess. So use after freeze, a double free, a stack smash, and even a format string bug will leave you with this thing where you control the ISA pointer or you control the object pointer into an Objective-C message send call. And the way you can recognize it is you see in a debugger, like you get a bad access within Objective-C message send. And after you've looked at a few of them, you can start to tell straight away the type of bug that you've got from the crash just by looking at like Objective-C message send plus 23 or plus 30, you know. So like for example, a double free is just a double invocation of the release method. So it just ends up being a method call on memory that's been freed, right? Which is the same for all these. And we'll look at format bugs later. Sorry. Okay, so dangling Objective-C message send exploitation in the original paper that I did, I used this technique to exploit it. So on the left, you can see like the object footprint itself with the is pointer at the start. And so we're assuming that as the attacker, we have control of this memory. So we point the is pointer to another piece of memory that we control. This can be through heap spray or an info leak or whatever, right? You can actually point it OX 20 bytes before the memory that you control because we don't actually use any of the initial elements in this process. So, yeah. And so basically what happens is the runtime takes the cache pointer, like we said, and then indexes it and reads out the mask. And in the technique that I provided, then the mask was set to 0. And if you remember in this diagram, it takes that mask and then adds it with the selector value shifted to the right 2 and uses that as an index. So a mask of 0 will generate an index of 0 in all cases, right? So this means that it will index just to the very first entry in the cache, which is still the memory that we control, right? And if we've hard-coded a selector value that matches the selector value passed into the function, it will just take whatever value follows it and then branch to it as EIP. This stuff is all in that frag paper that I mentioned, so if it's not clear, like feel free to go back and look at the details more detail, I guess. So this technique still works. All it does is returns a dangling Objective-C message send call into EIP control, right? So what's the problem? Why is this not relevant anymore? The first reason is because having control of EIP is only half the battle now. It definitely isn't a win. And to illustrate that, I guess, the last MacOS project that I worked on, we had like 5 or 6 exploits sitting with control of EIP, but none of those actually panned out into a fully working exploit. It wasn't until we had the info leak kind of construct to move forward, you know? So, yeah. And the reason in this case that you know, EIP control isn't win is because we have the mystery of what the cell value is. Now that modern OSs have a more randomized address space, then you can't count on hard coding a selected value anymore and using that to gain control. So we have to find some way around that. Although in local exploits, then if the selected value is stored in the shared region, which we'll talk about in a little bit, you can actually pull that out from a different process and then reuse that in the one that you are exploiting for local critic, right? And that was done by some of the Project Zero guys lately, if you want to see a public example of that. But another way that you can still use this old construct is if you combine it with an info leak of the text segment that the select is in, the module base that the select is in. And you just combine that text segment with the EIP control that you have and then just rock within that module to win. The problem is a standalone info leak now is pretty rare. Like in the process of finding that, you'll tend to find other bugs that you could just exploit more easily. So. Okay, so in this talk, I'm going to go over a solution to potentially convert the dangling Objective-C message send construct into an info leak, and also to find a way to execute code without even requiring the info leak at all. The proposed technique that I'm going to go over, it's different depending on whether you've got 32-bit, 64-bit, or ARM architecture, and also it's different depending on where the library is located that the selector is within. So the first thing I'll talk about is the shared region. And the shared region is a portion of the address space of all the processes on the system that's allocated for commonly used libraries, so they don't have to like remap them every time, right? And the way that works is a file /var/db/dyld shared cache. And that file is just all the common modules on the system combined together, and they just like map that straight into all processes, right? And in that directory, there's also a .map file, and that file contains like a listing of what's stored in the shared cache and kind of its order. So on both 32-bit and 64-bit platforms, the shared region is a fixed base, so that the allocation occurs at a fixed base. But on 64-bit platforms, then there's a slide added to the start, so the text file won't be mapped directly into the start. And the way the slide works is they take the size of the file and the size of the shared region, and they subtract one from the other to get how much space is left, right? And so on current platforms, that leaves 15 bits to play with for randomization. So I'm going to go over both architectures because they vary quite a bit. The reason I start with 32-bit is it's a little less complex, and we can go over it quickly. There still are quite a lot of processes on OS X that are 32-bit, so it still is relevant, even on a 64-bit machine. So the 32-bit processors use the old Objective-C runtime. There's no shared region slide, and the shared region actually starts at 0x9000000. So you can basically count on the shared region struct being there, followed by each module in turn. When that file is created to be mapped into the shared region, the way that, like, it's got a list of all the common modules that it needs to put in there, but it doesn't do them just in that order. It randomizes the order. So there is still some randomization with the shared region. You can't count on an address having a particular module remotely, right? So we need some way to figure out the unpredictable bits in the selector to look at the technique that we had previously, and then use those bits to create an index. And then we index into an array of buckets to the cache entries, and we use the fact that it's only selected the randomized bits to dictate which entry is the one that we want. It'll get clear hopefully in a little bit, but you can see down the bottom the bit pattern for a selector from my machine. So the start of the selector, 0x9, is always going to be fixed because the shared region is at 0x9, right? So we can count on those bits not changing. The last 12 bits are always going to be the same because they're the index into a page itself within the shared region, so it doesn't matter where in the shared region the selector is, because it's always going to lie at that offset of the page, right? So then those middle bits that are highlighted in bold, they're the ones that we care about, and they're what we have to somehow leak, right? So when we're generating a mask value to extract those bits, we have to account for the fact that the selector was shifted right by 2 before the mask was applied. So you can see below the mask that I've specified, OX3FFFC00. It just accounts for those bits that we can't count on shifted right by 2. And if you applied that mask to the selected value from the previous slide, you end up with a pretty big index of 3CFC00, right? So if you're able to predict, if you're able to find the address of a selector within a module, you can also count on the fact that somewhere relative to that selector is the text segment of that module, right? And that's where you can utilize gadgets. And so this diagram just shows, like, you've got a module loaded with the string table early on, followed by the text segment, and that's where our gadgets are. And you've got a relative offset to that. Okay, so the idea here is, for our fake object, we want to create a cache entry slide. And what that is, we want to generate all potential permutations of a selected value for those randomized bits. And by doing this, then, we can also use the same randomized bit value to our EIP value in each of those entries, right? So it's a huge slide of all potential candidates for the randomized bits. And so this diagram hopefully explains the technique a little clearly. This is the whole technique for 32-bit. So you control the ISA pointer again, and you point that to memory that you control. Both two columns on the right side would just be one large allocation that you control, right? So you've got the cache pointer pointing directly after itself, followed by the mask of 3FFFC0, which we figured out earlier would give us the randomized bits. And then below that, we've got each buckets in turn, starting from bucket 0 all the way through to, so the buckets are a series of pointers to cache entries, right? So we just have one pointer to each cache entry that we need to use. And then each cache entry is made up of incrementing the selector just of the randomized bits. So when the index is applied, we get it indexing into that big cache. We know that the selector will match up because we've just indexed using the randomized bits, and then it will branch relative to that selected to the EIP value at that location, which is the correct one for the slide, I guess, or for the randomized bits. And the caveat to this, as you can imagine, like we saw with the index, it's a pretty large allocation. You have to actually control an allocation which is the size of the buckets array plus the size of all those cache entries. And the size for the current shared region is here. It's 30E45000. You can actually still allocate that size from JavaScript and like in that kind of environment from programming languages. And one of the upsides of doing an allocation that size is that there's a limited number of places within the address space that it can be. You'll find that on OS X it falls really reliably into like one of a few places, and you can predict its address pretty easily. But as a downside to that, because you're doing these big allocations, you start to run into memory pressure bugs. And these bugs you'll see like in the debugger, you're crashing in like, a UD2 instruction or whatever, like, and they're generally not exploitable. But if you do hit these conditions, please report them to the vendor and get them fixed so that my technique can be more stable. Okay, so now we've looked at the 32-bit version of this technique, we'll go on to the 64-bit. And it's actually quite a bit different because they're not using the old runtime anymore. They've got a whole new version. And it's pretty crazy, like they've changed a lot of the Objective-C structs from just the old C-based versions that they were to be like this kind of bastardized C++ structs with methods that, I don't know, it's horrible to read, but it doesn't really affect us that much, so I haven't documented that too good. But for 64-bit modules in the shared region starts at 7FFF80000. Once again, the module order is randomized within the shared region. But in this case, there's a 15-bit slide, like I said, added. So the shared region doesn't start at that address. The mapping actually starts 15-bit slide added offset into that. Okay, so this is a logic diagram of the Objective-C message send function on 64-bit and how it's changed, I guess. Once again, they retrieve the ISA pointer from the start of the class footprint, and they read in the mask from that location. But this time they actually shift the selector prior to applying the mask by 4 to the left. So they actually make it like quite a big value. Then they compare indexing into the cache with that offset to see if they can find selector again. If they match it, they call the method as before, but if they don't, they subtract 16 from the offset and walk down the cache that way instead. So yeah, as you can see, like the mask changed from shifting right 2 to become a smaller number to like to the left 4. And that means that like if we were going to apply the technique from before to this, we would require a mask of FFFF0000, which would end up being like a 4 gig plus allocation. And like even if we're able to make that allocation, populating it is so slow that the user probably would have like browsed to another page or like done something completely different. It's just so unlikely to be feasible in real life. So instead, we have to use an alternative approach for 64-bit. And the way this approach works, instead of using the mask to seek directly into the cache, we use the mask to seek to the very end of our cache slide, and then we allow that Objective-C message send property where it subtracts 16 each time a negative match is found, and just let it iterate backwards through our cache slide until it finds the correct selector value. And this is it's only like a 4 megabyte allocation, so this is actually instant in real life. But there's some complications to it. When the offset's generated, they take the selector, as I said, shift it left by 4, and with the mask. Our offset has to be, somewhere greater than or equal to the end of our cache slide, so that if like the maximum randomized bit value was given, we'd still find the correct entry when walking backwards. But the mask value in that struct is only 32-bit, because obviously they never have this situation where the cache is like 4 meg big. So they limit it to 32-bit size. And so as you can see, like, this is a selective value from my box. And if you look at like the randomized bits that we don't know versus the ones that we can count on. So like obviously the 7FFF, that's the start of the shared region with the 9, but the rest of it, other than the last 12 bits again, is randomized. So it's like pretty similar, right? But after shifting it right 4, like with a 32-bit mask applied to the lower bits, we pretty much, the only fixed bits we have is this 1 bit that's highlighted and then the 12 bits on the right-hand side. If we were to try and count on those 12 bits on the right-hand side, we couldn't get a value big enough to hit the end of our cache. So like, if we tried to use that and index it to our cache, like I said, it wouldn't guarantee that we would get a match, right? So that, it means that we have to use that 1 bit at 0x80000 to guarantee that we get a fixed number. And that means that like whenever you apply that mask to any selected value, you'll always get the offset 0x80000. Because if we tried to mask the randomized bits and we got a fluctuating offset, then it would, it would work sometimes and not other times, depending on those randomized values. So that's why we kind of have to use that one bit in this case. And so this is, once again, an overview of the whole technique for 64-bit. Again, you control the ISA pointer. You point it this time 0x16 bytes before the, your allocation that you control. The first entry that you want to set up is the bucket pointer. And like this bucket pointer, you actually want to point 0x8000000 bytes before the end of your cache slide. So there's sample code for this, so if you're interested, you can look at this, probably more clear there. But so you point it like up into like whatever address your end of your cache is minus that, and then you set the mask to 0x80000, which we discussed before to get that one fixed bit. So then you once again create your cache slide through all permutations of the selector with randomized bits, and then with the appropriate EIP value for that same randomized bits in each one. And so what will happen, the mask will be applied to the selector. You'll get 0x80000 as the offset. It will add that to the bucket pointer and pointing it down at the end of your cache slide, and then it will walk backwards until it finds the correct one and calls it. Right. So the cool thing is it's much smaller than the 32-bit approach. It's only a 4 megabyte allocation, which is trivial, right? Also, like heap address leaks are very common compared to like trying to get the exact text address you want. And like I think at Black Hat like last year, someone demonstrated a way of using, there's always like timing attacks or different ways of leaking a heap address versus like text address having to find a specific thing. And also you can just spray and control a formatted portion pretty easily on OSX. So if the module isn't in the shared region, the way that it's loaded, basically when the dynamic linker, the executable file's been loaded, it gets handed off to the dynamic linker to pull out all the different dependencies that it has and load them in order. And each of those loads just follows the address that was used for the executable file itself, so they're all like at a fairly predictable region of memory. You can actually count on the load order in that Mocko header to know which order that the language will be mapped in at, and that kind of like eliminates some bits from the start. So you can just see like, there's more on this in my paper, but you can see like the values that I've given there. The default load address generated by the compiler is used for the executable file plus a slide, and that leaves like the bits that I've put X's, or the bytes that I've put X's for as the only randomized bits in those address. So you basically can just use the same technique for the shared region in this case, but with a smaller range to generate, right? Okay, so for an overview of the whole technique, basically what you're doing is tricking the runtime into revealing the random bits in the cell, and then getting it to branch EIP or RIP to the correct place in memory that you know is mapped and you know the contents of, right? So what do you do with that execution control? The first way you can use this is to take just one single gadget of execution and return the selected value that was loaded in the registers. So for example, when Objective-C message send finishes on a 32-bit platform, the ECX register contains the value that was passed in for selector, right? So if you control execution at that point and branch to a gadget like the one on the slide, you'll end up with ECX moved into the return, and then the method will just return the full selector value. And so if you're exploiting something where you have control of that return value, you've now just generated an info leak, right? And you can use that to re-trigger the bug with the cell value that you know. You can also do things like return to a gadget which writes the selected value into a region of memory that you control. So if you've heap sprayed an array of some kind of programming language that you are executing in the address space, and then you write it into there, you can then read it out from that programming language context and then reuse it to trigger the bug again. So same kind of thing. So another way to use this single gadget execution is to take that ECX value and then add it to each of the other entries in your RUP chain. I've never actually managed to do this myself, but a friend of mine did this in his exploit. I was pretty impressed. It's really hard to find a gadget that like lets you pivot and make modifications for the rest of your chain before continuing, but it definitely is possible, so I'm including it here. And then the other kind of easy way, if you can't control the return from whatever method was called, you can instead just find a gadget to write a fairly large value to a fixed location in memory. And so that way, if you can spray or whatever and control that address in memory, so for 0D, 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 for example, if you can position something meaningful there and then just write a large value, then you can then move forward with that construct. And so some examples of the kind of things that you would position there. If you're controlling a programming language within the address space like JavaScript, you might want to position things like an array buffer or a string import or just a normal array so that you can position their length field at a controllable location. And that way, if you just write a large value to the length field, now you're able to turn that into an arbitrary read-write construct of the address space, and that's way easier to finish than just having EIP, right? If you're not working with a language like that, you can look at since this is Objective-C, NS arrays and NS mutable arrays are also length encoded objects. They have a length field you can change, and then if that's the only way that they, test the bounds, then you can then read and write arbitrarily or whatever. And then just depending on the context of whatever you're exploiting, just look for length encoded primitives that you can position that way, right? Okay, so if you have generated a arbitrary read-write construct on OSX, a really handy way to utilize that is just to define the Objective-C segment within the Mocko binaries loaded in the address space, and then pass out the class ref section. And then you can basically do what the technique was doing earlier to find the cache pointer within that construct, and then walk the cache looking for a selector match. And then when you found a method that you want to infect, you just replace that function address with whatever EIP value you want. So in a situation where, for example, a JavaScript object wraps an Objective-C object, you might then be able to repeatedly modify and execute different locations of your choice or whatever. So that's pretty handy. Okay, so now we've looked at the technique for exploiting Objective-C message send dangling primitives, then we'll just look at some of the runtime changes that have happened since I wrote the last paper. The first thing that I ran into that was of interest, I think, is something called tag pointers. And what tag pointers are, they abuse the fact that the allocators will use natural alignment when they generate storage. So basically that means that the lowest bit in a heap address is not going to be set, right? Because they don't want to have things unaligned. And so the Objective-C runtime uses the low bit in the object pointer to indicate that instead of it just being a pointer to the heap as normal, it's actually a tag pointer. And the tag pointer stores the object contents inline, as well as a index into a list of different types of tagged objects, and then obviously the final bit is to indicate that it's tagged or not. As you can see that breakdown above. And that list there is the list on OSX of all the registered default tag types in the new runtime. Programmers can add types to this table, but I've never seen anyone do that in a real application. So. Okay, so the first type that I found pretty interesting was the NS Atom type. That 011 is the bit pattern for the last 3 bits that would indicate that a tag pointer is an NS Atom type. It's 01 for the type, and then the 1 just to say that it's tagged, right? And the interesting property of an NS Atom is that any method name that you call on the NS Atom object will just return 1. So you can call foo or does not exist, and it will just return 1 gracefully, and you won't have any problems. And that's super useful for continuation of execution and just overflows in general. I mean, if you think about overflowing into an NS array or something, then you have a bunch of pointers to objects, but you might only want to change 1. In the past, if you overflowed 10 before that 1, and they got used before you could make use of the override that you got, then you get a crash, right? Whereas now, if you can set them all to 1, set them all to be an NS Atom, then you have a much higher percentage chance of that method call not failing out. It just depends if they use the return of the pointer but also if you call a commonly used method name that would normally return a string, it will actually return an empty string as well. And you can see at the bottom, there's an example of just calling the init with UTF-8 string method, which doesn't exist obviously for the value 1. So it's like pointer value 1 called the method init with UTF-8 string lol. And you can see that the NS header just returns 1 cleanly without crashing, which isn't the case for everything else, right? Okay, so the next type, which was kind of interesting to me, is the NS string type. And obviously that was index 2, and you can see the bit pattern 1, 0 followed by 1. And in this case, the least significant byte was used for the length of the NS string, followed by the 101 pattern. And the way it works is any string that's less than 7 bytes, like contents-wise, is stored as a tag string. So it's stored in line in that pointer, and then obviously anything greater than that has to be stored in the old method on the heap with the normal runtime sort of pointer to it. And so, yeah, so in this example, it's just like simulating a 1-byte override into a tagged NS string, into an untagged NS string, sorry. So you can see, like, I initialize an NS string called x with the contents hello world. And since hello world is greater than 7 bytes, this is too big to be stored in a tagged pointer. So instead they allocate it out on the heap, put the contents there, and then have a pointer to it, right? And so you can see that like character pointer equals $x, and then write F5 to it. So that's, like I said, simulating a 1-byte overflow into the least significant byte of the object pointer. And because we wrote like the value, F5, we're guaranteed that the last bit will set, toggling this from an untagged to a tagged pointer as far as the runtime is concerned. And so the F before the 5 is considered the length of the string. So now if we printf the string length and just call the method length on it, or nslog the string, you can see like the string length comes out as F, like we'd expect. And yeah, so then instead of it going out to the heap and printing the context, it prints the other 7 bytes of the pointer, which we haven't overflowed. And so now we've generated a leak of that address from that construct, right? It's just from a 1-byte override to a leak. So another interesting situation is to go the other way. So if you have a small string of 7 bytes being allocated as a tag string, and then you overflow into the last byte of that, then you can change it from tag to untag, right? And so you can see that case there. I'm initializing the string with 7 A's, and then writing the value 0 over the last byte of it. And so then we call the method length again. And then you can see below the debugger output where it's actually dereferencing the contents of the string because they're stored in where the pointer is normally expected, and then trying to do a cache lookup on it. And so you can see like it's crashing, dereferencing 41, 41, 41. So if you're able to control the contents of a 7-byte or less string, then a 1-byte overflow turns that into a controlled dangling dangling Objective-C message send construct, right? And like the technique that we talked about earlier is how you would go about taking that from there to finish it. Okay, so an NS number is another type that is pretty useful in a very similar way. And the NS number bit pattern would look like 111. So it's like 3 indexes of the table followed by the 1-bit set. And it's pretty much the same as NS string. You can see an example here. I initialize a number using the value deadbeef feed face. And obviously I picked that number so that I would make sure that it was too big to be stored inline in a pointer, right? All of the bits of the 64-bit value are used. And so then I simulate the 1-byte override again and change it to F7. And this time that's changing it into a tagged NS number. And then I print its contents with the unsigned long value method. And so yeah, because it used to be allocated on the heap and now is being treated as a tag pointer, it once again like prints the contents of its own pointer and you get it in for leak again. So there's on 64-bit ARM devices, then there's this concept called non-pointer ISA or non-pointer ISA. And I haven't actually done the research yet on this. I was planning to do it before Infiltrate, but I got pretty busy and didn't manage to look at it. But if I do find anything interesting here, then I will post it later on a blog or something. Basically, instead of the object pointer being tagged on 64-bit ARM, the ISA pointer is tagged. And you can see there's a bunch of metadata stored in line in the ISA pointer. And just at a glance, some of the interesting fields extra ref count or has C++ detour. Like they sound like they could probably be useful, but I haven't gone that route yet to figure that out. So another thing that was added to the runtime since I last wrote about it was Arch, and Arch is automatic reference counting. So Arch is basically a little bit like garbage collection, but rather than being done at runtime, it's done at compilation time. So the compiler actually keeps track of reference counts of objects and then inserts, releases, and retains, depending on how the object's used, right? And unfortunately, this mitigates quite a lot of potential use after free bugs because, like, Arch is way better than the developers were at managing ref counts. But there's still a lot of libraries that are compiled unsafely without Arch, and so all these constructs still exist in that. And as I mentioned, like, the dangling Objective-C message send construct doesn't just come from use after free, and there's a ton of other ways to end up in that. So, I mean, pretty much every Objective-C app that I've looked at in the past 10 years has had dangling Objective-C message send calls in some way, right? Just put this in here because I really like this technique, I guess, but it was documented publicly by Ilya a bunch of years ago. Apple decided to remove %n to make the format string bugs safe. But after they did that, they went ahead and added %&, and that basically means treat the value passed in at the stack as an object pointer and then call a method on it. So if you control the format string, obviously you can use %& to generate a dangling Objective-C message send construct to wherever you want. It's pretty cool. You can still use direct parameter access with %& on OS X. So you can just use it to find a pointer on the stack to a large allocation that you control and kind of skip one level of indirection there, and then just use the technique. Okay, so another thing they added is called blocks. And basically, they decided they need to improve C and add Lambda functions. It's a pretty irritating syntax, I think, but you can see it there. That's declaring a block called myBlock that takes an integer, and then it's just returning the integer multiplied with multiplier, which was on the stack outside of the block. So they have some constructs to copy variables from other contexts into the block for use, right? So when I first saw that, I just kind of assumed that it would be just a trivial case of a call instruction to some new text segment like instructions that implement that, right? But it's actually like quite a bit more complicated than that because even in a C program, they've made the block a fake Objective-C object. And they've done this by implementing this block literal struct. And you can see it down the bottom, it's got an is a pointer, just the same as a normal Objective-C object. And that is a pointer points to a object definition or class definition for different objects depending on, or different classes depending on the scope of the block. So for example, a block declared on the stack will have an NS concrete stack block base class. One on the heap will have NS concrete malloc block, and then one in like the BSS or data segments will have NS concrete global block. Just a little tip, when you're reverse engineering, if you're looking for places to overwrite, you want to see where blocks are used in your binary, you can just xref the references to these base classes and then you'll just straight away see blocks. And that's not limited to Objective-C apps, right? These can be used in anything. So you saw in that structure there was a method called invoke, and basically that method is called when you call the block, right? And that just points to the main body of the block code. So as far as exploitation context, like if the block is invoked prior to like stack checks or something, then you can use them as a way to get EIP control by overflowing the invoke method. The struct itself can be stored on the stack, on the heap, wherever. In the case of a stack smash, then usually the pointer to the block struct is positioned in a way that you'll hit that before you hit the struct itself. So rather than overflowing the invoke method directly, you're going to overflow the pointer and then have to like point that to some fake setup class that you control, kind of in the same way you exploit a v-pointer override. It's just one additional level of indirection prior to EIP control, right? And like I've seen cases where you can use this to defeat stack cookies. The reason I put this in here is I know a lot of people like have been exploiting a C or Objective-C program and just hit this construct that just looks like a v-pointer override and go, what the hell is this? And yeah, this is usually what it is. So index instance variables are not actually new. They existed when I wrote the last paper. But what has changed is the way that developers are using them, I think. And in a couple examples I've seen, well basically index instance variables exist so that like classes can be dynamically sized. And all that means is like, instead of having just ibars for all the data in your class, you might have like one ibar that points to the rest of the class. An example is an NS array, because the contents are going to be dynamically sized. NS array can't be allocated like up front, like it doesn't know its own size, right? And so instead they use these index instance variables. It's pretty confusing. Like I hit an app recently where a developer was using index instance variables just to hide its private data, because a lot of people will just use class dump and dump out all the meta information from an Objective-C binary and quickly see all the classes, right? So by using these, you know, misusing, I guess, these index instance variables, they can hide their private variables. And the only way that I've seen to figure out what they are is to look at the accessor functions for that area. And it's nice because Objective-C has a lot of metadata, so accessor methods are all named, and so if you see like, you know, get serial information or something, and then that function just indexes 20 into the struct where there shouldn't be anything, and pulls something out and uses it, you know, like kind of what that variable is. Okay, so while I was on stage, hopefully if the frac stuff okay at using computers, then my paper got published as well on frac.org. So personally, I have a lot of trouble like with pulling technical stuff from a talk. Like, I love going to conference talks and seeing like what can be done, but I also like really love being able to follow up and read the paper afterwards. So that's why I decided to publish at the same time. I guess like the paper has everything here, and I guess more detail and some sample code. So if you're interested, feel free to check it out. Does anyone have any questions?
Your 64-bit technique looks more convenient than your 32-bit technique. Is there any reason why you wouldn't use 64-bit technique on 32-bit?
Yeah, there is. It's kind of, yeah, it's, let me go back to there, I guess. Well, okay, so did you see in the 64-bit class struct, there was a buckets pointer, and that buckets pointer was controllable by us? Well, like, the order of the mask being applied to selector was different in 32-bit and 64-bit. If you wanted to just, it would result in every time it wanted to iterate through the 32-bit cache, it would reapply the mask, and that would result in it like only looking at that one place. So it ends up in an endless loop just repeatedly. It doesn't actually walk down, whereas the 64-bit with the order and the mask, it's more clear if you look at the structs, but will actually walk. You can actually use that endless loop for like, if you can like change memory and brute force it repeatedly, you know, and it will just look in the same place until that hits the right value, then that works. But yeah, that's the reason. I know that wasn't very clear in the slides, and you did ask that before, but yeah, that's the reason.
That was a good question. Who is next? All the hungry people are staring at you like.
Yeah, I'm hungry too.
Cool. All right, so thank you very much.
Thank you.